lab partner, we nailed this. This is awesome data. I gotta tell you, lab partner, this is the best you and I have ever done. In fact, I did a percent calculation error. We got less than 1/10 of a percent of error in a lab where we're measuring numbers with thermometers. That's like, wow, that's awesome. We did awesome, okay. Now lab partner, it's gonna be a little bit confusing, so I'm gonna go through some of the calculations. And when I go through these without doing them for you, you need to do them, but I gotta show you how to do them, so this is gonna be kind of tricky, okay? So here we go, lab partner. If we take a look at the calculations, determine the temperature changes for each of the reactions. Well, that's easy. Just take the before and after temperatures and you write those down. That's temperature change difference. Just write down the before and afters. All right, let's go to B. B, calculate using the volumes of liquid and delta T values, then calculate the heat released in joules for each reaction. Okay, you're gonna need an old buddy calculation, temperature equation, and that temperature equation is Q is equal to M delta T CP. All right, we've used it before. You need this again. This is going to help you find the heat for each one of the reactions. You have to do this 3 times. So I'll go through one of them with you. Okay. So the Q of reaction 1. I need the mass in reaction 1. Now in reaction 1 we added 4.09 grams of sodium hydroxide to 100 milliliters of water. What's the mass? Well, the 4 grams got dissolved, but it's still 4 grams, and you had 100 milliliters / grams, because remember a milliliter of water is a gram. So you had 100 grams of water with 4.09 grams of sodium hydroxide. Combine those, get your total mass of the solution. So that would be 104.09 grams. What's your change in temperature? Just look at the 2 numbers, subtract them for temperatures. You had 33.0 and 23.1. That's a difference of 9.9 degrees Celsius. 9.9 degrees Celsius. All right, we need the specific heat capacity, and it's water. It's a water solution. Does sodium hydroxide change it? No, not significantly at all. So no. So it's, I mean, if you had a lot of it in there, it could, yeah, but it's just basically water. So 4.1, I rounded to 4.19. So I'm gonna use 4.19 for the specific heat capacity of water. And that's joules per gram degree Celsius. I'm not putting my units in here. Maybe I should, but I'm old, so I'm not doing it. So multiply these 3 numbers together. The grams and degrees Celsius will cancel out from these 2 values, and you'll be left with joules. So if I multiply those out, you'll get how many joules of energy was released in that first reaction. So you go ahead and you do that out. And I did this out earlier, and actually I don't have a calculator with me. I had to use my phone. I was doing it earlier. Let me see if I find one. I don't think there is one here. There's not one. Okay, so you do that out, and you came out with 4,000 something. You came out with maybe 4,000 and something. It's 10 times, that's times 4, 10 times. So yeah, it's 4,000 and something. So you get 4,000 blah, 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 blah joules. All right? So 4,000 blah, blah, blah joules. You do that math. Okay, you're gonna have to do the same thing for reaction 2 and 3. This is reaction 1. That's reaction 1. Do reaction 2 and do reaction 3. Using the same equation. So the same equations used in all 3 of these reactions because you're figuring out the heat released by each reaction. Let's just take a look at reaction 2. In reaction 2, you need the mass of the solution. Now in that reaction, we added 50 milliliters of HCl and 50 milliliters of NaOH. What are the masses? What are the masses? They're water solutions. Okay, 2 molar water solutions. So we're going to use 1 milliliter, but it's not pure water. I know, but it's very much close enough for government markets. Not going to be much different at all. So 50 milliliters of acid and 50 milliliters of NaOH is the same thing as 50 grams, because it's virtually all water, and 50 grams virtually all water. So we're going to take those 2 50s and add them together, and we get 100 grams. For the second calculation of the reaction, 2. So calculation 2, or I actually labeled these as B, so let me stick with the letters. B, calculation B, part 2, reaction 2. You're going to use 100 500 grams. All right, the 50 and the 50. Then the temperature change, you're going to put the temperature change in there. The temperature change looks like it was 14 degrees. You put the 14 degrees in there. And you need the specific heat capacity of acid, which is basically water. So what is it? 4.19. But it's not water. It's basically water, so it's 4.19. So use 4.19 for the specific capacity of that solution, and you're going to put 14 in there. I'll go ahead and do this for you. I'm not going to do this out for you. I remember I did this, and you come out with like 5,000 something, because that's 400 times 14, so 5,000 something. So you'll come out with 5,000 blah, blah, blah joules. All right, so the same thing for reaction 3. Reaction 3, you're going to take the mass. Now here's what we did. We took 4.19 grams, and we added it to 100 milliliters of HCl. It was 100 grams of HCl. So 100 grams of 4.19 grams, your total mass is 104.19. A little different than this, but be accurate here. I'm telling you, if you be accurate, this thing, we nailed this flat burn. We nailed it. All right, so you go ahead and put the temperature difference in there. There's a difference around 24.2 degrees, 24.2, and it's 4.19 once again for that solution and its specific heat capacity. You do that out, and you come out with like 10,000 and something. Right? This is 10,000 blah, 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 blah joules. Okay, that's part B. That's the most labor-intensive part for the calculations. Part C, it says calculate the moles that you used. Now, we all remember how to do moles, right? Yes, we do. Yes, we do. Let's see. I'm going to keep this up here. So moles. Can you see this left, partner? Yeah, you can. We all remember moles is mass over molecular weight. So for each one of these, for the sodium hydroxide, you're going to take the mass of the sodium hydroxide used and divide it by the molecular weight of sodium hydroxide. Now, sodium hydroxide, NaOH, you go ahead, you add that all up, and you'll get the mass of the sodium hydroxide. I'm not going to do it for you, my partner. You go ahead, you look this stuff up, and you get a mass for that sodium hydroxide. That's your molecular weight. So you'll divide. Well, actually, not the second one. The second one was liquid. The first and the third one, those two, reaction 1 and reaction 3, we used the pellets. Remember the pellets. So put the mass we used. The pellets in the first one was 4.09 grams. So we take the mass and put 4.09 divided by the molecular weight. You've done that right. You've added all these up and came out with the number and put that on the bottom. Divide and get an answer for how many moles of sodium hydroxide we used. Be accurate on this too. Let's see. 1, 2, that's 1, 2, 3 significant digits. So be accurate to 3 significant digits. So it's going to be 0.10 blah blah. Okay, round the 0.10, round that next number after the 0 off, and then use that number for your moles. So this moles and this moles are done, and by taking now this one down here, the reaction 3, we use 4.19 grams. So put that on the top, 4.19, and then divide by that number that you got by adding all those numbers up. Yes, you did. You went to the periodic table, you looked them all up. Good job, lab partner. You know that number. I'll give you a hint. It's a nice round number. And divide, and do these out to 3 significant digits. So 0.1 blah blah. So make sure you put those 2 numbers after the 0.1 in there. They do make a difference, and they will come out to be sweet if you do that right. So get your moles. Okay. Take the molecular weight, divide it in 4.09, 4.19. Get those. Now this one here. And you'll see on here, I even wrote this down for you. It says, determine the moles for reaction 2. Determine the moles using the volume and the molarity of the sodium hydroxide solution. So that means we all remember molarity is equal to moles divided by liters. So how am I going to get moles? Well, it was a 2 molar sodium hydroxide solution. 2 molar. So put 2 molar here. And for the sodium hydroxide, how many liters did we use? not the acid. This is one we took 50 milliliters and 50 milliliters and add them together to get 100. But only one of them was 50 milliliters of sodium hydroxide. So put the 0.05 down here on the bottom. 0.05 down here in the bottom. That's 50 milliliters of the sodium hydroxide, and multiply and you get the moles. And well, that comes out to be like a boom, 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 spot on number. All right, now the reason you need those 3 mole calculations is for the next part, part D. For each reaction, calculate the heat released in joules per mole of NaOH, and that's what we want, joules per mole of NaOH. Now, wait a minute. So these calculations that we did for reaction 1, 2, and 3 using the heat equation for part B gave me how many joules of heat was released. Calculation C gives you how many moles of each one of these steps, reaction 1, 2, and 3, that we use to get those reactions of sodium hydroxide. So now what we want the amount of joules per mole for the sodium hydroxide reaction. Joules per mole. So this is joules per mole. So you're going to take for calculation D, so for calc D, you take calculation B and divide it by calculation C. Calculation B and divide it by calculation C. That's your joules. Calculation B divided by your moles of sodium hydroxide, and you'll get the amount of joules per mole. That's what we nailed it. Now, here's what we should be doing. Well, actually, let me take a look at this first. E, the equations for the 3 reactions are given in the background information. So I did put those out. I put the equations down on the front for each one of the 3 reactions that we went through. This is reaction 1, reaction 2, and reaction 3. Those are the reactions. So I'm going to ask you a little bit about those in a second here. Take a look at them. Okay. The equation for each reaction given in the background. Rewrite these equations as net ionic equations. Rewrite these as net ionic equations. So I'm going to go through that, but before I do, let's just take a look and write this down. You've got these calculations done. What I want you to do is when you get calculation D for each one of the reactions done, take your joules divided by your moles and get a number for that. Check this out. This is a Hess's law lab, meaning that this was a partial reaction, reaction 1. This was a partial reaction, reaction 2. And overall, reaction 3 is an overall reaction for reaction 3. If you take these 2 reactions and combine them, you get reaction 3. And Hess's law says you can do a direct analyzation of heat generated by the overall reaction and get a value for it, or you could do 2 separate partial reactions and get their heats, add them, and you should get the same thing as the overall reaction. Check that out. When you take your calculation for D, so take your joules divided by your moles, and you get a number for that, this comes out to be like 48,000 something. This one comes out to be like 50 something. I got like 52,000. And this one comes out to be just a little over 100,000. When you do these, if these 2 added together should be very close to this because of the same. This are the 2 half reactions, and this is the overall reaction. And if you add up the amount of heat for these 2, you should get that. We nailed it, lab partner. We nailed it. We came within like less than 1/10% difference. We're good. We're good. You're good. You're my best lab partner I've ever had. Yes, you are. All right, so just wanted to point that out. Okay, now, so I'm going to get rid of this. Okay, I'm going to get rid of this. In fact, if we go ahead and look down here to calculation G, using your experimental results, find the sum of H1 and H2, reaction 1, heat of a reaction for 1, heat of a reaction for 2. That's what I was just telling you to do. That's what you're going to do. You're going to take these 2 values that you get for calculation D and add them up. And then you're going to compare them to this one. So that's that calculation right here. And then F, show that the net ionic equation is equal. So let's look at the equations, because for E and F, it's talking about the equations on the front page. Okay. So A, B, C, and D, get your numbers. And then G says, add these and compare it to that. Okay, so that's what we got. And that's the last calculation. Then we have some discussion questions back here. I mean, I'll just point something out to you right here. Discussion question number 1. It says, do your experimental data for reaction 1 and 2, do they come out to be the same as the overall reaction for reaction 3? And I had said here, if your results are less than 5,000 joules apart, actually, that should say 5,000 joules per mole. That's what that should say. I forgot to put the per mole in there. 5,000 joules per mole. Then you can consider this close enough for government work. We got way less than 5,000 difference. We nailed it. Okay, so that's what that's referring to. We nailed it. Go ahead and finish out the rest of those discussion questions, but that's what question 1 is referring to. Compare to reactions to reaction 3. All right. It's not corona. Okay. It's dry throat, which is not corona. I mean, it's not. All right. So let's take a look at the reactions on the front page. So I'm going to erase this. Hope you got that down. If you didn't, rewind. Okay. Clean this mess up. Feel bad because the floor is so nice and clean. Okay, take a look at the reactions on the first page.